Hello, my name is Mr. Asprey and this is June 2019 EDEXCEL Paper 1, and I have now done all the papers for Pure Maths for EDEXCEL, so you can watch the playlist. I'll link it right now. Let's get into it. Let's go. Right, so we've got a function and it says that given that x plus 3 is a factor of f of x, find the value of a. Well, if x plus 3 is a factor, then we know by the factor theorem that f of minus 3 is equal to 0. Okay, so f of minus 3 is equal to 3 minus 3 cubed plus 2a times by minus 3 squared minus 4 times minus 3 plus 5a, and that is equal to 0. So this gives us minus 27 times 3 is minus 81. Minus 3 squared is 9 times 2 is 18. This gives me plus 12 and plus 5a. Okay, so what does this give me then? It's a total of 23a, and this would be minus 69 is equal to 0. So 23a is equal to 69. So a is equal to 3. Bosh. Question number 2. We have a cos graph where x is measured in radians. And it says use diagram 1 to show why cos x minus 2x minus a half is equal to 0 has only one real root. Okay, we're rearranging this so that I have the cos x on one side and then the corresponding function that I'm going to draw on the graph on the other will be positive 2x and plus 1/2. So that equation is the same as the one they've given us. So I've just moved those two terms over, which means I can draw the cos graph on the graph, which it already is, and I can draw also 2x plus a half. So 2x plus a half would look something like this. It would go through here at a half, and we're going to need to estimate another point in order for us to draw a line. So let's look at x is equal to pi over 2. So we know from the cos graph that this will be the x-coordinate of pi over 2 because that's when it hits the x-axis. Now if I were to multiply that by 2, I would get pi, and then add a half, I would get pi plus a half. Pi is 3.1, so about 3.6. So my graph should go through, or my straight line, sorry, should go through this point here. So, and I know it will go through this point here. So this would be an accurate representation of the line y is equal to 2x plus a half. So I'd write y is equal to 2x plus 1/2, like that. Okay, perfect. And we can see that it's only going to cross at one point. It's going to cross right here. So this is our only root. So it does say give a reason for your answer, and what I would do is I would say that y is equal to cos x and y is equal to 2x plus a half intersect at one, or should I say exactly one point. Therefore, cos x equals 2x plus a half has only one real solution, and so does cos x minus 2x minus a half equals 0. Right, that covers all bases, definitely getting the marks for all that explanation. Fantastic. Given that the root of the equation is alpha and alpha is small, use the small angle approximation for cos to estimate the value of alpha. Okay, no problem. Well, we know the small angle approximation for cos. That's given to us in our formula booklet. And that is 1 minus the angle, which in this case is alpha, squared over 2. So that's cos x, and then we'll also need to take away 2x, so that's 2 alpha, minus a half as well. And that equals 0. Okay, so I'm going to get 1/2 here, minus alpha squared over 2 minus 2 alpha equals 0. Let's multiply everything through by 2, just to tidy this up a little bit. And then let's bring it all over to the other side because I like to have my x squared positive. Like that, okay. And then we can just go to our calculator solver. And I can type in polynomial degree 2, and we have 1, 4, and we have minus 1. And this gives us minus 2 root 5. And of course, as well, minus 2 plus root 5 and minus 2 minus root 5. So which is going to be the correct solution? Well, let's just look over here. We can see that that purple dot there is going to be a positive value. It's going to have a positive x value. So therefore, I know it must be this one, my correct answer, because that one's positive, the other one is negative. Lovely. Oh, just spotted that it did say to 3 decimal places, which is a bit strange. I don't know why they've asked that, but fine. It would be then, oh, that's the negative one. So it would be the positive one, which is 0.236. I've got a year 2 differentiation question here. I've got to use the quotient rule because this is a quotient. So I write y is equal to u over v. U is the numerator, which is 5 squared plus 10x. And v is the denominator, which is x plus 1 squared. Okay, I have to differentiate each of these separately. So this one gives me 2 times 5 is 10, drop the power down, and then drop the power down just to get 10. And here, dv by dx, I'll use a chain rule here. So the 2 comes down to the front, keep the bracket the same, drop the power down by 1, and then times by the derivative of the bracket, which is 1. So I don't need to do that, and I don't need to write that either. Lovely. Okay, so dy by dx, and the formula is in your formula booklet. It starts with v, which is x plus 1 all squared, multiplied by du, which is 10x plus 10, minus u, which is 5x squared plus 10x, times by dv, which is 2 lots of x plus 1. And that's all over v squared, which is going to be x plus 1 squared squared. And if I'm squaring and then squaring again, that's the same as raising it to the power 4. So I can write that as to the power 4, like that. Okay, I'm going to want to do a bit of tidying up here. So the first thing I'm going to do is I'm going to divide each term by x plus 1. So there are 2 terms on the top line. When I divide the first term, this green one, by x plus 1, that's going to cancel out this squared. That's going to cancel out this whole thing there. Again, the second term is this all yellow term here. And then that's also going to knock down a power here to 3. Okay, so now let's write out what we have. We have x plus 1, we've got 10x plus 10, and here we have 5x squared plus 10x times by 2, and that's all over x plus 1 cubed. So now what we can do is, I guess we can expand. Yeah, we've got to expand that top row. We can't do much else really. This is going to give me 10x squared. I'm going to get a plus a 10x. I'm going to get plus another 10x, and I'm going to get plus 10. Be careful with the negative, but I'm going to get minus 10x squared, and I'm going to get minus 20x as well. Okay, I'm going to keep writing out the denominator each time, just to keep it algebraically correct. Okay, the 10x squared cancels with the negative 10x squared. The 10x and the 10x cancels with the negative 20x. So it looks to me like I've got 10 over x plus 1 cubed. So a is equal to 10 and n is equal to 3. Perfect. Hence deduce the range of values for which the derivative is less than 0. Okay, right, so how do I make this less than 0? How do I make 10 over x plus 1 less than 0? Well, if I look at a fraction, the only way that I'm going to get something being negative is if either the numerator is negative and the denominator positive, or vice versa. So here, this numerator is 10. That's never going to be negative. So if I want the whole thing to be negative, then the denominator has to be negative. So I really just need this denominator here to be less than 0, which means I need x plus 1 to be less than 0, which means I need x to be less than minus 1. And we're done. Okay, question number 4, we've got your classic type of binomial, and it's just asking us to do the first 3 terms. Okay, so I'll just get some space down here, and I will write it out in bracket form. So it was 4 minus x, and it was 1 over, so you can see it here, can't you? So it's 1 over, so it's a negative power, and it's also square rooted, so it's a half power. So it is to the power of negative a half. Okay, first thing we do, we need to pull out the factor in order to make the constant term inside the bracket 1. So we have to pull out a factor of 4, divide by 4 inside the bracket. But when we do that, we must pull out the power as well. So it becomes 4 to the negative half. And this becomes 1 over x minus, so 1 minus x over 4. Okay, good. Next step would be to write that as half power square root to 2, and then negative power means reciprocal, so 1 over 2. And then we can use the formula. If you don't know the formula, it is in the formula book. It looks something like, not like that, it looks something like this. N minus 1 x squared over 2 factorial, and then n minus 1 n minus 2 all over 3 factorial to the x cubed. So we start 1, n is the power, so that's negative a half. So I'm adding on negative a half times by x, which is the variable inside the bracket there. So in this case, I need to times it by negative x over 4. How many terms did they want? Did they say 3 terms? First 3 terms. Okay, so I just need to do one more. And that will be n minus 1 all over 2 factorial times by minus x over 4 squared. Okay, so we'll do it term by term. This first term will give me plus x over 8. This term, I'll do on my calculator. Okay, and I get 3 over 128, and that will be x squared. Okay, and then the final thing is don't forget to multiply through by that half. So this becomes my answer. Okay, and we can go straight down to this next part of the question where it says the expansion can be used to find an approximation for root 2. Possible values of x that could be substituted into this expression are, okay, without evaluating the expression, state giving reason which of the three values of x should not be used. Well, if you can see here, the purple or pink variable x over 4, that needs to be the modulus of that needs to be less than 1, always. That's what it has to happen in order for the binomial expansion to be valid. Now we can forget about the negative sign because the modulus will take care of that, and we can times both sides by 4 like this, so it tells me that x needs to be less than 4, or the magnitude of x, sorry, the modulus. So this one is no good. Okay, the x value has too big a magnitude for it to work there. So I would say that x equals minus 14 is not valid as the magnitude of x needs to be less than 4. Perfect. State given a reason, which of the three values of x would lead to the most accurate approximation of root 2. Okay. So basically the smaller the better. You get a more accurate approximation the smaller value of x you use. And in terms of small, I mean the magnitude needs to be small. So this one would be the best. So I can say that x equals minus a half is best as it is closer to 0 than x equals 2. Lovely. Question number 5, we need to complete the square. So I'm going to take out a factor of 2 by x squared plus 2x and then plus 9. I'm then going to complete the square here, which is going to give me x plus 1 all squared minus 1 squared plus 9, which is going to give me 2 lots of x plus 1 all squared. 2 times minus 1 is minus 2, and then plus 9 is going to give me plus 7. Perfect. Next, I've asked to sketch the curve. So I'm just going to draw a quick axis here. And the first thing I can spot is that it's going to have a y-intercept of plus 9. So I'll draw that there. The turning point will be where x is equal to minus 1. That will make this bracket here 0. And that will leave y is equal to 7. So I'll draw the turning point there. Minus 1, 7. And that's it. Just draw a quadratic that goes through these points. Great. Okay, next. That's part B. Let's move on to part C. This is where it gets tricky. Describe fully the transformation that maps the curve with that equation onto the curve y is equal to g of x. Now you could do this by literally drawing these two on your calculator, the original one and then this one, and solving and finding where the minimum point is and then showing the translation. But what I'm going to do is I'm going to do it algebraically, and I'm going to spot that here we've got and x minus 2 has been subbed in, but here we don't. But this can be rearranged so that we do. So I can write g of x is equal to 2 lots of x minus 2 squared plus x minus 2, but there are 4 x's there, so I'm going to have to do 4 times x minus 2. And if I were to do that, then that would be the same as x minus 2 minus 8. But I want it to be minus 3 in total, so I'm going to need to add 5. And that will give me the same function as up here. And now all the x's have been placed with x minus 2's, so that means a translation by the vector. So x minus 2 means 2 to the right, so 2 to the right. And before we had a y-intercept of 9, and here we're going to have a y-intercept of 5, so it means it's gone down by 4, so minus 4. So that is the translation. Again, what you could do is you could just sketch this on your calculator, solve for the minimum point, and then work out what the translation is. Okay, find the range of h of x. Well, h of x is 21 over the completed square that we had here. Now, the completed square has a minimum value of 7, as we can see from the graph there. So that's the smallest it could be. So that's what I'm going to try first. So when x equals 7, we get h of x is equal to 21 over 7, which is equal to 3. And then every other value that comes out of this completed square is going to be greater than 7. So let's try and sub in a larger number. So let's try and sub in, for example, 100 and see where we get to. So 21 over 2 lots of 100 plus 1 squared plus 7. Okay, so that implies that we are tending to 0 because that's a very small number. And what we could do is we can then change it to maybe 10,000. And you can see here, again, tending to 0, becoming very, very small. So the range of h of x is it's between 0, but not equal to 0, and 3, because it can equal 3. Okay, question 6, and we've got a classic trig equation in order for us to solve. First off, it is in degrees, and I've spotted a double angle here, so that's where I'm going to start. I'm going to start by saying that we have what is sine 2 theta. Well, we should know from our double angle that sine 2 theta is 2 sine theta cos theta. So times that by 5 gives me 10 sine theta cos theta. And this is equal to 9, and tan theta is sine theta over cos theta. Okay, so next step would be to multiply through by cos theta. And that will give me cos squared theta is equal to 9 sine theta. And then top tip here, I wouldn't divide by sine theta. I mean, you can, but you have to be careful about the solution you miss. Instead, what I like to do is move it all over to one side, like this, and then factorise. So I can factorise out a sine theta here, and that gives me 10 cos squared theta minus 9 is equal to 0. Okay, so when you have a factorized expression like that and it's equal to 0, then each factor itself will equal 0, or could equal 0, should I say. So sine theta could equal 0, or 10 cos squared theta minus 9 could equal 0. Okay, so let's think about when is sine theta 0. Well, hopefully you can just visualize the graph, and we know that sine theta looks like this and like that, between minus 180 and 180. So when is it equal to 0? Well, minus 180, 0, and 180. So because all of those are in the range, we can say that we're going to get solutions like this. Okay, now this one takes a little bit more work. I'll add the 9 to the other side and then divide by 10. So I get cos squared theta is equal to 0.9. I would then square root, and the square root of 0.9 is going to be 3 root 10 over 10, and that's plus minus, because when you square root the plus minus appears. Okay, so we're going to have to do each one separately. So let's start with the positive one, and let's first off make sure that I am in degree mode, and then do cos to the minus 1 of the answer. So I get 18.4. 18.4. Okay, and then as soon as I press cos to the minus 1, I will do 360 minus the answer, because that is what I need to do for cosine. 341, and that's outside of the range that we require. But I'll write it down anyway, just so I can explain what I'm going to be doing next. And then once you have the first two, you can then move, add or subtract 360 from each of those. So if I've spotted that if I subtract 360 from this one, I will be in the range. So that's what I'm going to do. And that gives me minus 18.4. Okay, great. So this one can be deleted, it's not in the range. And that's all of the ones that I'm going to get from that. And then what I can do is I could do cos to the minus 1 of negative 3 root 10 over 10. And that gives me 161.6. I do 360 minus to get my second solution. And that is outside the range, but once again, if I take away 360 from that one, then that will be inside the range. And we can see this symmetry that we get with the cosine graph as well. Okay, so those are my solutions. I'll just highlight them nice and clearly. So 1, 2, 3, 4, 5, 6, 7. Deduce the smallest possible solution to the equation blah. Okay, well let's see what the transformation is. That's what I like to do with these types of questions. So theta has turned into x minus 25. Okay, so basically what I've done is I've just subtracted 25 from my input. Okay. So when I solve this equation, what I would end up with is, rather than theta equals, I'll end up with x minus 25 equals all of these solutions, which are minus 18.8. Actually, that's not the smallest, is it? Let's do them in order. Minus 160, 61. Oops. Why are you messing up? Stop it. Minus 161.6. We'll get minus 18.4. We will get 0. We'll get 18.4. And there'll be some more other ones, won't there? But we're looking for the smallest positive solution. Now what I need to do next is I need to find x, I need to add 25 to each of these terms. So when I add 25 to the first one, I'm going to get something like minus 136.6, I think, whatever. But when I add 25 to this one, this is what's going to give me my first positive solution. Plus 25, which is 6.6. So that is the answer. That is the first that's the smallest positive solution. Okay, job done. Okay, question number 7. We've got a simple model. The value V of a car depends on its age. The following information is given, blah, blah, blah. Use an exponential model to form, for the car A, a possible equation linking V and T. Okay, so what does an exponential model look like? Well, it looks like the value is equal to, what's the best way to do this? Some constant, I would use A, but that's not great here. So some constant B times by E to the KT. That's what an exponential model looks like. Normally I'd use capital A, but I just didn't want to confuse it with this capital A here, so I've used capital B. Okay, so let's then substitute in values. So we know that we've got 20,000 is equal to B, E, and that's when it's new, so T is equal to 0. Okay, so that tells me that 20,000 is equal to B, because e to the 0 is just 1. Okay, so next we have that 16,000 is equal to B, which we know is 20,000, e to the KT, and we know that that is just e to the k, because t is 1. Because it's after the value after 1 year. Okay, so 16,000 divided by 20,000 is the same as 16 over 20, which is the same as 4 over 5. And that's equal to e to the k. So taking the natural logarithm of both sides, I get the natural logarithm of 4 over 5 is equal to k. Okay, great. So now I can say that the actual equation is that V is equal to B, which we worked out was 20,000. E to the, does it say anything like that? So ln of 4 over 5 t. Okay, that is my equation, job done. Next, it says the value of the car is monitored over a 10-year period. Its value after 10 years is 2,000. Evaluate the reliability of your model for this information. Okay, so after 10 years. So for part B, we will say t is equal to 10. So our model will predict that the value of the car will be equal to this. So I'll do that on my calculator. I'll do 20,000 multiplied by e to the power of 10 times, I'll just do that first just to avoid confusion, ln of 4 over 5. Okay, and then close those brackets. Okay, so that should be nice and clear. Okay, so that's looking quite good. 0.5. Let's do this. It's money, so let's do 48. Okay, and that is pounds, I believe. So they said it was 2,000. So what I like to do in this situation is I like to do the estimated value minus the real value, and then divided by the real value, and then times by 100. This gives me the percentage error. So this is a really good way of evaluating a model. So I'll take that and I'll subtract it from 2000. I'll subtract 2000. I'll divide by 2000, and then I will times by 100. And I get 7.37% error. I would say that's a relatively good model, really. So I would say that 7.3% error is relatively small. Therefore, a good model. Anything less than 10%, I would say it's quite good, really. I mean, anything more than 10%, that's not good. Okay, part C. It says the following information is available for car B. It has the same value when new as car A. Its value depreciates more slowly than that of car A. Explain how you adapt the equation found in A to use it for car B. Okay, so let's look at the equation. Well, this represents the starting value, which will stay the same because it tells us the starting value is the same. But this constant here, that's what influences how fast the depreciation is. So that value is it's a negative value. Obviously, you can check that on your calculator. So it looks something like that. Yes, there you go. That's a negative value. Now, the more negative that number is, the quicker the model will depreciate. We want this new model to depreciate more slowly, so we would need to choose a less negative number. So I would say replace the ln 4/5 with a less negative number, and that will slow down the depreciation. Okay, part A says show that the area R1 is 20/3. We know this is the curve it's given to us here, so we know its roots when it equals 0 are 0, -2 and 4. So this must be -2, this must be 0 of course, and this one here must be, this one here must be 4 where it crosses the x-axis. So R1 is between -2 and 0, so it means I'm going to be integrating between -2 and 0. We always put the number which is greater along the x-axis at the top. So 0 is bigger than -2, so we put that one at the top. And we're going to integrate this function here, which when expanded will be x cubed, and we will get a -2x squared, and we will get a -8x when we expand that bracket, or those brackets. Great, okay, then we integrate that of course, so we up the power and then divide by the new power, up the power to 3 and then divide by the new power, up the power to 2, divide by the new power gives us 4, and we're subbing in 0 and -2. Okay, when we sub in 0, well, all of these terms have got an x in, so that's just going to give us 0. And then we take away the second bracket as always, and then we sub in -2 in here. So -2 to the power 4 is 16. -2 to the power of 3 is -8. There's a minus there, so that will turn it to +8. Times it by 2 gives me 16, and then put that over 3. And then -2 squared is 4, times by -4 is -16. Okay, and this will equal, you're given 20/3. Perfect. Okay, that's part A done, and then let's move on to part B. Okay, part B is a bit tricky because well, eventually we're going to have to use the actual answer to arrive at the answer they want us to, which is never really recommended, but I've checked the mark scheme and it's okay for this. Anyhow, we've got B, and we need to find this value B here, for which the area of R2 and R1 are the same. So if we were to integrate between B and 0, the same function as before, because it's the same curve of course, okay, this will give us the same area, but because it's under the curve, the value of the integral will be negative, so it'll be equal to minus 20 over 3. Okay, so integrating is going to give me, again, and we've already done this, so it's x over 4 minus 2 over 3 x cubed minus 4x squared, and that's equal to minus 20 over 3, and that is between b and 0. So subbing in b is just going to give me b to the 4 over 4 minus 2 over 3 b cubed minus 4b squared, and then sub in 0 is going to give me 0, and that's equal to minus 20 over 3. And then we can multiply 3 by 12, which will give me 3b to the 4 minus 8b cubed minus 48b squared, and then add that over, times it through by 3 and then by 4, so I get plus 80 equals 0. Okay, and then this is why I find it a bit tricky, is that you have to multiply this out and show that it's the same as this, which in essence is showing that it satisfies this equation. But it feels like a little bit of a cheat. But that's what I'm going to do. So multiplying out that one will give me b squared plus 4b plus 4. And then I'll need to multiply it through by this quadratic. This is going to give me 9 terms, so timesing the b squared first will give me 3 b squared to the 4 minus 20b cubed, and then plus 20b squared. Then timesing the 4 b's will give me plus 12b cubed minus 80b squared, and then plus 80b, and then multiplying the 4 is going to give me 12b squared, and then minus 80b, and then plus 80 is equal to 0. And then we'll need to collect up the like terms. So we've got a b to the 4, perfect. We have cubes, we've got minus 20 plus 12, which is a total of minus 8, which is great. So we've got 3b to the 4 minus 8b cubed. And then let's look at the squareds. We've got plus 20 minus 80 is minus 60, plus 12 is minus 48. Great. And then finally, or not finally, but the b's are going to cancel to get 0, and then the plus 80 at the end. Great, and now this is exactly the same as our equation which we found by doing the integration, so therefore we can say that yes, we have verified it to work. Now, say you weren't given this and you were asked to solve this, a little trick which you might be able to do is, the reason I've kept this part A at the top here is this actually tells us that b plus 2 is a factor, as it shows here, and that's because I can rearrange this integral by flipping these over, and when you flip the limits, all it does is turn the actual value negative.
because rather than doing 0 take away minus 2, you're doing minus 2 take away 0. So that, in essence, tells me that B has a solution equal to minus 2, because when the minus 2 is on top and the 0 is on the bottom, it's exactly the same as this one. So B could equal minus 2, which means B plus 2 in brackets is a factor. So you could divide through by that, and that might help out. Okay, on to part C, and let me grab some more space. Okay, part C, and it's asking us to explain with the aid of a diagram the significance of this root, 5.442, when they've already told us that the value of the root here, B, is 1.225. Okay, so let's draw the graph, and let's just draw the positive part. So it comes in there, and then it goes like up here, like that. And we have here that this region in here is 20 over 3. But the value of it when we integrate is negative, because it's below the axis. And then we need to find another root where all of the area is going to give me negative 20 over 3. And we're told that it's here at about 5.42. And we know that this is here 4. So if I were to integrate between 5.442 and 0, the function, I would get minus 20 over 3. Okay, so let's call this area here, the green area, R3. That's below the axis. And then let's call this area here R4. That's above the axis. Now, when we do this integral, we will be including both parts, obviously, because it's from 0 all the way up to the end of R4. And R4 will have a positive value. Whoops, let's say R4 will be positive, because whenever we integrate above the axis, we get positive values. But R3 will be negative, because whenever we integrate below the axis, we will get a negative value. And we'll have to add those two together, and we'll get an answer of minus 20 over 3, which means that R3 is bigger than R4 by a difference of 20 over 3.
Okay, question number 9. And we have a log equation. A is greater than b is greater than 0, and show that a is equal to b squared over b minus 1. Okay, well, let's just rearrange this log equation. So when I've got two logs, one subtracted by the other, I could write that as log of a divided by b, like that. And now we have both sides written as a single logarithm. We can remove the logs, essentially. So I get a over b is equal to a minus b. Multiply both sides through by b. Gives me this. Because I want to make a the subject, let's move all the a's to one side. Let's reduce the number of minus signs as well. So I'll plus the b squared to that side, and I'll minus the a to that side. So I get b squared is equal to ab minus a. I'll then take out a factor of a to make a the subject, and then I will just divide through by that new factor b minus 1, and there we have it. B squared over b minus 1 is equal to a. Great. Okay, part B. Write down the full restriction on the value of b, explaining the reasons of this restriction. Okay, well, first off, I can see that we have here that b is one of the inputs of the logarithms, and all inputs for logarithms need to be positive. So I know that b needs to be greater than 0 due to log b being part of our equation. I also know here that we've got there, we can't be dividing by a negative, so b cannot equal 1 due to b squared over b minus 1. And finally, we also know that a must be positive because a is also an input. Right, so that means that b squared over b minus 1 needs to be greater than 0. Now the top is a squared term, so that will always be positive. So the bottom needs to also be positive. So b minus 1 needs to be greater than 0, which means that b needs to be greater than 1. And with all of that combined, the only way that all of these three things can happen is just if b is greater than 1. Because that will satisfy the condition that it needs to be greater than 0 and that it doesn't equal 1. So this is job done. Okay, question number 10. This is a proof question. And again, I've seen lots of students get this one wrong, so that's why I've put it in there. And it's just a standard skill also that we need to know. That in order to prove something, most of the time it's a good idea to show for evens and for odds. Because if you show for evens and odds, then that's all the numbers. Happy days. Okay, so what I'll do is I'll say let n equal 2k, which shows that that's an even number. And then what we'll do is we'll say that then n squared plus 2 is equal to 2k squared plus 2, which is equal to 4k squared plus 2. And we can say this is equal to 4 lots of k squared plus 2. And we can say as 4k squared is a multiple of 4, then 4k squared plus 2 is not a multiple of 4. Okay, right, and then what we do is we say let n equal 2k plus 1, which is an odd number. Then n squared plus 2 is equal to 2k plus 1 all squared plus 2, which is equal to 2k plus 1 times 2k plus 1 plus 2. So that's 4k squared plus 2k and 2k makes 4k, plus 1 times 1 is 1, plus 2. So this is 4k squared plus 4k plus 3. So we can factorise out the 4 from these two terms here, like that. And then we can say as 4k squared plus 4k is a multiple of 4, 4k squared plus 4k plus 3 is not a multiple of 4. And then, this is where lots of students forget to write the conclusory statement. We can say we have proved n squared plus 2 is not divisible by 4 for all even numbers and for all odd numbers therefore, therefore it is true for all natural numbers. We must write that at the end if you are wanting to get the full marks. Otherwise you miss out on a mark if you don't write that conclusory statement right there. Okay, feel like I've written an essay there, but I want to get all those marks, and I just want to make sure that the examiner does not penalise me at all. Given that x is a real number, the value of the modulus of 3x minus 20 is greater than or equal to the value of x minus 9. State, giving a reason, if the above statement is always true, sometimes true, or never true. Okay, so let's just write that down. So that would be the modulus of 3x minus 28 is greater than or equal to x minus 9. Okay, so I'm going to try x equals 1. And this gives me 3 minus 28 is minus 25, which is equal to 25, which is greater than or equal to x1 minus 9, which is minus 8. Okay, so that works for that. Now, is there a number where it doesn't work? Because all we need is just one number. And let's go for something like, well, when is this the smallest it could possibly be? And that's when x is equal to 28 over 3. So when x is 28 over 3, then the modulus part is 0, and this one is positive. So that doesn't work, because 3 lots of 28 over 3 minus 28 is not greater than or equal to 28 over 3 minus 9. Because this side, the left side is 0, and the right side is negative. So it doesn't work. So therefore, the answer is sometimes true. Wallop. Okay, next question. Geometric sequences. And this question, you have to take a lot of care over it. A competitor is running a 20-kilometer race. She runs the first 4 kilometers at a steady pace of 9 minutes per kilometre. After the first 4, she begins to slow down. In order to estimate her finishing time, the time that she will take to complete each subsequent kilometre is modelled to be 5% greater than the time she took to run the previous one. Okay. Show that her time to run the first 6 kilometres is estimated as this. So the first 6 kilometres, well, we know the first 4, she will be doing it in 6 minutes. So that's 24 minutes. And the next one will be 6 minutes multiplied by 1.05, because there's going to be a 5% increase in her time. So without getting too techie with this, I'm just going to work out them and add them up, basically. And then the next one will be 6.3 times 1.05. So just times that by 1.05. Again, slowing down is going to give me this. And then I'm going to add these all up to get a total time. So 6.3 and then plus 24. And that's going to give me 336.915. And 0.915 times by 60 is going to give me that in minutes. So take off the 36, times that fraction by 60. sorry, that's going to give me how many seconds there are. So that's 54.9 seconds. So total time is 36 minutes 55 seconds to the nearest second. Perfect, 2 marks in the bag. Okay, part B, it says show that her estimated time to run the half kilometre for kilometre 5 up to 20 is given as this. Okay, so the 5th kilometre would be 6 multiplied by this increase in time, so that's to the power of 1. Then the 6th kilometre, we would do that to the power of 2. And the 7th kilometre, we would then again multiply it by another 5% increase. So we can see here that this value here is the R value minus 4. So again, 2 is 6 minus 4, and 3 is 7 minus 4. So we can say, therefore, the rth kilometre is equal to 6 times 1.05 to the power of R minus 4. Can't really do more than that really, just that's it. It's a bit of a rubbish question if I'm being honest. Estimate the total time in minutes and seconds she will take to complete the race. Okay. So kilometre km 1 to 4 we already know takes 6 times 4, so 24. And then after this, we've got a geometric sequence. So we need to go from, we know that let's call the first term after these 4, so the 5th term, will be 6 times 1.105, which we know is 6.3. Okay, and after she's done these 4 kilometres, then she has a total of 16 kilometres to do. With the first one that she does after the first 4 is going to be 6.3 minutes. And the ratio we know is increasing by this amount each time. So the sum up to 16 is equal to, we know the formula is this. This is given in our formula book. So we can do 6.3, 1 minus 1.05 to the power of 16 over 1 minus 1.05. Okay, so let's do that on our calculator. Okay, so typing that in gives us 149.04. So the total time is equal to the 24 at the start plus this 149.04. So I need to add on 24, which obviously gives me 173.04. And they want that in minutes and seconds and multiply it through. So if I do multiply this by 60, I get 2.526 seconds, which rounds to 3 seconds. So the actual answer is 173 minutes and 3 seconds. Okay, we've got a function and it's asked us to find essentially the turning points of that function. So I'm just going to go down here and just going to write the function out again. So I've got a bit more space. So it was 10e to the minus 2.5 x sine x. Now this is a product, So I'm going to label or colour each side like that, and what I'll do is I'll write u is equal to the green part, like so, and v is equal to the pink part, like this. We then differentiate this. Now the input of that is minus 2.5. X, the derivative of that is minus 2.5. Times that by 10, and that gives me minus 2.5. E to the minus 2.5 x, because when we differentiate e, it just stays exactly the same, including its input. And dv by dx, sine differentiates to cos. Okay, so product rule tells me the derivative is equal to u times dv, so 10e to the minus 2.5x times by cos x, plus v times by du by dx, which will be sine x multiplied by minus 2.5 e to the minus 0.25x. Great. Let's factorize, and we can take out a 2.5 e to the minus 0.25x. Easy for you to say. And we get this. So what is left inside the brackets? Well, I've got to times the 4 to make 10. And I've also got to times it by cos x to get that term there. And then what about this next term? Well, there's a minus in front of the 2.5. And I've just got to times it through by sine x. Okay, and remember also we want the derivative equals 0 because we're looking for the stationary points. Okay. The e function can never be 0. Exponential functions can't equal 0. They do not cross the x-axis. But this bracket here can. So let's set that bracket equal to 0 to solve this. Okay. And then what we can do is we can move the sine x to the other side. Divide through by cos x. And we get sine x over cos x. Which is equal to tan x. And that, I believe, is exactly what they asked for. Tan x equals 4. Perfect. Part B, where it says that the sketch of this, of h against t, okay, so we've just got to do that sketch. So, I'm going to do it up here so that we can see it alongside this graph. So I'll just draw an axis like this. I'll label this one t, this one h. And because it's the identical function, but it's just we've taken the magnitude, or the modulus, sorry, what we're going to do is the top part, the bit which is above the x-axis, is going to stay exactly the same, unchanged. The bit below the axis is going to get reflected up to become positive, so it's going to look like that. And then this this third bounce here is going to look exactly the same. This next one is going to get reflected up, and then this one here is going to look exactly the same, and then finally this last one is also going to get reflected up. So it's going to look like this. Okay, great. Right, it now says that the function is measured in meters, which is important. And it says find the maximum height of the ball above the ground between the first and second bounce. Well, let's look at where that is. So the ball starts here, it goes up, and then it comes back down here and it bounces there. And then it goes up again and it bounces for a second time there. So in between those two, that is the maximum height there. So we're looking for the second turning point. So let's go back down here, and we know that turning points occur when tan x equals 4. So I can take tan to the minus 1 of 4 to get my first value. In fact, this is it's now t, isn't it? Okay, so I just need to do that on my calculator. Now, just to let you know, we have to use radians here, even though it doesn't specify in the question. If we're modelling with trig functions, we're going to be using radians, unless specified that we're not. So there we go, that's the first t value. Now the second t value, well, you know what to do for tan, we add on pi. Okay, so we get 4.467. Okay, so that's what we're going to sub in, because we want to find the height, not just the time at which it occurs, we want to find the actual height. So the formula was 10e to the negative 2.5 t, which we're going to replace with our t value, because reminder, again, it's the second bounce we're looking for. Or it's the time in between the first and second bounces, so it's the second t value we're going to use. Okay, so we just need to type that into our calculator. I won't bother with the modulus sign, I'll just turn it positive at the end. So it's 10e to the power of negative 0.25 times answer, times by sine of answer. Okay, we get a negative answer, which is to be expected because that part of the graph used to be below the axis, but the modulus is going to reflect it up to make it positive. So it's 3.17, or let's go 3.18, and that is meters. Okay, perfect. Right, part D. Explain why this model should not be used to predict the time of each bounce. Okay, well, what you'll notice is that the time between each bounce stays constant because it's a trigonometric function which is modelling it, and the gaps between the periods of trig functions are the same. This wouldn't be the case in real life because as the ball goes up, it's going to go up less high each time, so it's going to come down quicker, so the bounces should become more close together in reality. Okay, so we can say that in reality the time between bounces should decrease after each bounce. The model does not account for this. Job done. Okay, question 13, and we have a function here with some unknowns, but it says that it passes through this point and has two vertical asymptotes with the equations x equals 2 and x equals minus 3. Explain why you can deduce that q is equal to 4. Well, if it has a vertical asymptote, it means that we were dividing by 0. So that covers that part. So let's figure out this part. We know that x equals 2. So we can say that at x equals 2, 2x minus q equals 0. So that means 4 minus q equals 0. So q equals 4. Next it says show that p is equal to 15. Well, we're then going to have to use this other bit of information we're given, and that is that the x value is 3 when the y is a half. So subbing that into the equation, we're going to get a half is equal to p minus 3 times 3 over 2 times 3 minus 4, and then times by 3 plus 3, which is 6. Okay, great. So this bottom bit here is 6 minus 4, which is 2, times 6, which is 12. Times the 12 up to this side, we get 6 equals p minus 9. So therefore p is equal to 15. Great. And then part B just basically says work out that area and give your values like that. Well, if I want to integrate y here, you can see that the bottom is 2 factors, so we need to split those up and do partial fractions. So I'm going to start off by saying 15 minus 3x over 2x minus 4 x plus 3
is equivalent to a over 2x minus 4 plus b over x plus 3. Multiply through by the denominator and we get this. And then let's let x equal minus 3. 15 minus 3 times minus 3 is 24. This one cancels. Minus 3 times 2 is minus 6. Minus 4 is minus 10. So this implies that b is equal to minus 2.4. Next, let x equal 2. That's what solves that bracket. We get 9 here. And we get 2 plus 3 is 5, so 5a. And that implies that a is equal to 9 divided by 5, which is 1.8. Okay, great. So now we need to set up our integral. So we're going to be integrating 1.8 over 2x minus 4 minus 2.4 over x plus 3, and we're going to need to find our bounds. So we know here the x is 3, and here this is where y is equal to 0. So solving from the top, we had 15 minus 3x. We want the top to equal 0, and that means that x equals 5. So this right here is 5. So we're going to be integrating between 5 and 3. And this is with respect to x. And we can actually simplify this integral down a little bit, because we've got a factor of 2 on the bottom there. So we can write 0.9 over x minus 2. Okay. Now these are luns. The derivative of the bottom is just 1. So we're going to integrate this, and it's going to be ln of x minus 2. As long as we take out a factor of 0.9, then the top will be 1, which will be the derivative of x minus 2. So we're going to get 0.9 ln x minus 2. And again, here the derivative of the bottom is 1. So if I take out a 2.4, then I'm left with 1. So minus 2.4 comes out. And now I can just integrate that to ln of x plus 3. And again, this is between 5 and 3. So we're going to sub in our limits, and we're going to get 0.9 ln of 5 minus 2, which is 3, minus 2.4 ln of 8, minus 0.9 ln of 3 minus 2 is just 1, and minus 2.4 ln 6. Okay, so let's simplify. 0.9 ln 3. Ln 8 is the same as ln of 2 to the power of 3, which is the same as 3 ln 2. So this is going to give me minus 7.2 ln 2. Ln of 1 is 0. 2 minuses there make a plus, so plus 2.4 ln 6. Okay, and just a reminder that they want it in terms of ln 2 and ln 3. So this ln 6 is a bit awkward, but we can split that up, because ln 6 is equal to ln 2 plus ln 3. So we get plus 2.4 ln 2 plus 2.4 ln 3. And let's look, how many ln 3s have we got? We have 3.3 ln 3, and we have minus 4.8 ln 2. And we're done.
Question 14. Right, I love this question. I actually did this question as one of my tricky questions like a year ago. But I'm going to do it again because I like it so much. And also, I think I've come up with a better way of doing it. Anyhow, we have find dy by dx at the origin. Okay, so I'm going to differentiate with respect to y, which will give me the x by dy. And that will give me, well, first off, let's look at the input. It's 2y. So the derivative of the input in respect to y is 2. So 2 we multiply by the coefficient to make 8. And then differentiating sign goes to cos, and we keep the input the same. Fantastic. And then what we can do is we can flip over. So we get 1 over 8 cos 2y. And then we can say that dy by dx at the origin, which is where y equals 0, is equal to 1 over, cos is 1 at the origin, so it's just 1 over 8. Okay, fantastic. Part B, use small angle approximation for sine 2y to find an equation linking x and y for points close to the origin. Okay, well, we know that x is equal to 4 sine 2y. When y is small, then the small approximation for sine, well, we know that sine theta just is approximately theta. So sine 2y is approximately 2y. So it's 4 times by 2y, which equals 8y. So rearranging to make y the subject, I get x over 8. Okay, and then the next part says explain the relationship between your answers A and BI. Well, the gradient is 1 over 8 for both. So, yep, y equals mx plus c of this y equation, the gradient is an eighth, and also when we differentiate, again, the gradient is an eighth. Okay, so next one, it says show that for all points lying on C, dy by dx is equal to this in terms of x. Okay. So what I'm going to do is I'm going to use a good old triangle method. Okay, so I'm going to draw a little triangle like this. And I'm going to put 2y right here. Okay. Now, what do we know? Well, we know from over here that sine of 2y is equal to x over 4, just by dividing both sides by 4. And that's perfect. That's all we need. So sine is the opposite over the hypotenuse. And remember we said that sine 2y was equal to x over 4. Okay, we can use Pythagoras' theorem to get 4 squared minus x squared square rooted. Because we know by Pythagoras' theorem that to find the short side we take the hypotenuse, square it, and subtract the other short side squared and then square root. Okay, now what do I need? I need dy by dx. I really need cos 2y, don't I? Well, what's cos 2y? Cos is the adjacent to this triangle, which let's write 16 here instead, over the hypotenuse, which is 4. Okay, let's times both sides by 8. In doing so, this gives me 2 lots of this, because we cancel the divide by 4 and we need an extra times by 2 to make 8. And then let's take the reciprocal. So I get 1 over 2 lots of the square root of 16 minus x squared. Fantastic, and this is what dy by dx is, because dy by dx is 1 over 8 cos 2y. So I can say dy by dx is equal to 1 over 2 lots of the square root of 16 minus x squared. So when I did this a year ago, my tricky question, I went a longer way round. I am all for the triangle method now. So much cleaner. Okay, hope you enjoyed that. Bye for now.